Okay, we're on. Good morning, everyone. Thanks for making it back for day 2. So today we're going to carry on, with introductory topics, and we're going to get into what's important from linear systems. How's that? And we'll continue with that probably into next Tuesday. Just a couple of updates. Let's see. So thanks. Most of you have signed up for one-to-one meetings. Had a few yesterday. Very nice. The office hour looking like the best time that gets the most people is going to be in Friday afternoon, which is okay. But if you haven't contributed to the doodle poll yet, please do by tomorrow. So whatever information I have tomorrow afternoon is what I'm going to base the selection of the office hour on. And of course, and it probably will be that, not everybody is available at that time. If that doesn't work out, we can set, you can certainly contact me to set up an appointment at another time, or I might, depending on how things go, we might set, 2. We might do one Thursday afternoon and one Friday afternoon, if that seems to be what's going to work best. So we'll see. Stay tuned. Okay. So other than that, thank you for doing assignment 0, which again doesn't count for anything, but just a little exercise to get people submitting on Moodle, for those of you who haven't done that very much, and B, just checking out your MATLAB status, because we will be using MATLAB quite a bit. Okay. Anybody have any questions, anything at this point? Okay, if not, we're going to kind of pick up where we left off here, which was just this, we were discussing some of the different tasks that we might be looking at in signal processing. And, we looked at an example, for example, noise reduction. That's a pretty obvious one. Artifact reduction. We were kind of talking a little bit about feature detection. So this is kind of where we left off. And this is, this is largely, well, you can take a whole course in this. Okay, so we're just barely going to touch on this later in the course. And this is, I guess today we might be calling this artificial intelligence or machine learning, but it's we used to call it statistical pattern recognition. Some still do. And the methods, have been around for a while. But basically, the idea is, and this is true in a lot of biomedical applications, right? You want to find an event or a thing that happened. You want to be able to identify that while you're monitoring a signal, right? And maybe you want to set off an alarm, or maybe you want to record something at that time. So, a feature is something that communicates some form of information. And let's just say, as a simple example, we have an ECG signal and we want to just record, we want to be able to automatically identify the peaks for purposes of computing, automatically computing heart rate. That's maybe a pretty simple thing to do. And that would actually be very easy in this signal, right? Because you could just set a threshold here and say, okay, well, if it gets above a certain level, that must be one of the beats. And so we'll record that as a beat. But it's not always that simple, and especially in the presence of noise, which might, kind of artificially push you above or below the threshold. you're probably going to want something that's maybe a little more robust sometimes. And so, we'll be discussing some of the ways to deal with those kind of things. But again, we're just barely going to be able to touch on that topic. And then another one that actually, is actually a big part of biomedical research, especially, is modeling. And the idea being that, through simulation and things like that, we try to model physiologic systems in order to, well, for a variety of things, to understand them better, to test out hypotheses, on things that maybe would be too expensive or difficult to do in an actual living system, at least early on, and things like that. And so a lot of the things that we look at in signal processing can be used to model physiologic systems because the math is the same. And you may or may not have been exposed to this idea in say linear systems or circuits, but there are a lot of things, a lot of types of systems that are not electrical in nature that use the same differential equations basically as electrical components, and so are sometimes modeled with circuits or equivalent circuits. And so there are resistances and compliances. So this is an example of a fluid system, basically the lung, and pleural pressure. And people, in a simple version of this model, people will model this as a resistor for the airway resistance to flow, and a compliance, which would be like a capacitor, which would basically, model that aspect of the response. And so in this system, which is not electrical at all, the input is pressure, P of T, and the output is volume of the lung. So, that's, nothing like a circuit or anything like that. And yet, we can model it with an equivalent circuit and basically substitute different quantities for the voltage and current. And the reason for that is because the equations are the same. Okay, so this can be done with mechanical systems. It can be done with thermodynamic systems, and they all, end up having equivalent types of circuits to them. And so there's a big kind of area, or maybe it's more of a tool in a lot of different areas of biomedical engineering, where people will do this approach to modeling. Some of this may be a little older, I guess, but people still do this. We have more sophisticated computer systems now, and so, but even these things are also taken into finite element models, where basically you model a large system as broken down into a lot of smaller pieces, which could be resistors, capacitors, etc. So there's a lot of this aspect done. We'll see some examples of this, but we won't spend a great deal of time on it. So this course is called Biomedical Signal Processing, and there's not really any particular distinction between processing biomedical signals and any other signals. But there are some things about biomedical signals that are kind of common among them. Let me roll out my little pad here. Let's see. There we go. Okay, so some typical things about biomedical signals that we will try to address somewhat. One is that they generally have low frequencies. Now, there are exceptions to these things, but biomedical signals that you're detecting, are generally the frequency content is, in the low hertz range, and we aren't dealing with things like radio frequencies and stuff like that. An exception, of course, is instruments that are designed to work that way, like MRI or ultrasound, where we're operating in the megahertz of signals. But for the most part, signals we're detecting from biological systems are going to have low frequencies. So that, from that standpoint, some aspects are less demanding, but on the other hand, there are other things that are problematic, such as we typically have poor signal to noise ratio, and you might as well get used to that abbreviation if you haven't seen it before. SNR, noise, sorry. So they're noisy, right? And if you've, and hopefully in instrumentation class, you've seen that. And one of the big tasks that we have to deal with is trying to remove noise as much as possible without damaging the important information, the important signal information too much. Another one is that because we're trying to, in detecting biological signals, we're trying to couple something non-living to something living, using a transducer of some kind. Very often we end up with the problem of baseline drift, because we don't always have good coupling, and it varies because living things tend to move. And so we will see this problem also. And what I mean by that is that if you had a beautiful signal that adhered to a nice solid baseline like that, that's what we would like to see. Okay. However, let me see if I can, oops, sorry. Where's my, oh, it looks like I can't change color right now. Okay. But what often ends up happening is actually our baseline can drift around. And so our signal kind of does its thing relative to the drifting baseline. So it might do something like that, right? And what we'd like to do is to kind of remove that baseline that floats around and get a signal with a nice flat baseline. And there are methods we can use to try to get there. But that's going to happen a lot in these kind of systems. Okay. And so hopefully, intuitively you can see it would be much easier to analyze this signal than that signal. Okay. And then finally, the other thing, and we mentioned this before, is very often we end up with artifacts of other processes. Because our biological systems are complex and they're doing lots of things, and there's a lot going on that is not just the thing that we're measuring. And so often it's hard to measure only the thing that you're trying to measure without picking up properties of some other process going on, right? And an example of that we looked at last time was an EMG signal taken in the rib cage for some of the intercostal muscles picks up electrical activity from the heart, and you can't do anything about that because the heart's there and it's generating a lot of electrical activity, but you don't want it, right? You're interested in the muscle activation in the rib cage, and so you have to find a way to do your best to separate those things if you're going to get to the information you want. So those are kind of typical things that happen a lot in the biomedical field that that you don't necessarily see as much in other applications, but you might. Any questions on that? Okay, so that ends that set of slides. By the way, when I make annotations on slides, I will save the annotated versions and they will be posted. So you'll be able to get my annotations. Okay. All right, so that's, sure. Okay. So that ends the slides that we were hoping to finish last time. And these are the slides that are posted for today. Okay. All right. Okay, so now we're going to dig into linear systems. Okay, and again, stuff that, so as noted, there's a lot of stuff in linear systems where you do a lot of math and very often it's not clear what it's useful for. So what I'm trying to do here is to pull out the stuff that's actually going to be important to us as we kind of move forward. And so, these are all things that, pop up in a typical linear systems course. And so we will address them. Okay. First things first, a linear system. We should have a idea of what that is. And basically, this is going to kind of characterize the relationship between inputs and outputs. Okay. And so if we say an input F1 gives us an output G1, and an input F2 gives us an output G2, then what has to be true for that linear system? Well, we'll say it in words first before the math. A linear system basically means that we're going to, well, our output can be characterized as a weighted sum. Well, let me say that another way. Okay. If we have a weighted sum of inputs, our output will be characterized by a weighted sum of their individual outputs. Okay. So I will, well, we'll see if someone will jump in with an answer to this. So if an input F1 gives G1 and F2 gives G2, then what can we say if this is a linear system? Can someone jump in?
Yeah, you could,
go ahead. Oh. Okay, I'll just answer.
We'll let Alex go. Okay.
So like alpha times F1 plus beta times F2, and then you insert that into the system. The output should be alpha times G1 plus beta times G2.
Sorry, my pen's getting a little crazy here. G1 beta G2. Yeah, and actually it's important to put these scaling factors in there. A lot of times people neglect that. Try to make that a little more alpha-like, a little more F-like. Okay. So yeah, that's mathematically saying, hey, if I have a couple of inputs and I add them together and put them through the system, I should get the sum of their individual outputs. And they can be scaled by, in this case, scalars alpha and beta, and I should have the same scaling contributions at the output. That's a full definition for a linear system. Now, that has to be true for everything that I put through the system, right? if the system is linear, this is going to be true across the board for whatever inputs that I could use. Okay. So, you know, I mean, that makes it easy to disprove if you can find an example where this isn't true, right? But, you know, for it to be true for a system, we would have to test all possible inputs, which we would never do, right? On the other hand, you know, depending on what's inside that system box, if we know what's in there, then we will have some idea that it can be at least reasonably characterized as linear. And in a lot of cases, and especially this is true with circuits, right? They are linear over a certain range of operation, maybe not for everything, but for a, you know, restricted, say, set of inputs, say between certain voltage levels and things like that, they operate linearly. So a good example is an operational amplifier, right? That if you took instrumentation, you've probably seen an operational amplifier. You know, we consider them to be kind of this, when you work with them, a lot of times you use some ideal assumptions and you assume that they're linear, but they only operate linearly over a certain range. If you get outside of that range, it's no longer guaranteed. Okay. But for our purposes, okay, linear system, we're operating in the linear range, and this is going to be true. Okay. So if we have a system and we know it's linear, this is actually going to simplify a lot of things, and that's helpful. Okay. So hopefully that's fairly straightforward. Then we have this other property, and it is a separate property. Okay. You probably have heard it referred to as time invariance, but I'm going to change that. I'm going to call it shift invariance because shift invariance is more general, and that's the way we talk about things in imaging. And so it applies to time signals as well as, say, images, which are spatial signals, and anything else. Okay. So, you know, if you're used to talking about things as LTI, linear time invariant, we're going to be saying LSI, linear shift invariant. Understand that it means the same thing. Okay. Okay. Now, for a shift invariant system, the implication is that its properties don't really change with time. We'll say time in this case because we're talking about time signals. So we have a system, and an input f of t gives an output g of t. Then what do we expect to happen if, let's say, we have an input f of, we'll say, t plus delta t? What do we expect to get? Someone who is not Alex.
It'd just be g of t plus delta t.
Sure, that's simple enough, right? For all inputs f of t, and frankly, and all delta t, right? Basically, if we have an input and we get an output and then we move that in, you know, we do that same input at a different time, we should get the same output just at that later time, okay? And it shouldn't matter at what time we do that experiment. So the system, and again, in words, the system's response doesn't really change with time. Okay, that's, again, a fairly simple concept, but note that that is separate from this, okay? Because those two things can exist separately from one another and they don't depend on each other. Okay. However, when we have both of those together, linear shift invariant, then a lot of things become very easy to work with in our system. Okay. So So now if that's the case, basically making the point that they are separate things, you can have all of the permutations of that. In other words, we can have linear shift invariant, we can have nonlinear shift invariant, linear shift variant, nonlinear shift variant. The easiest thing to work with will be the linear shift invariant systems, and we're going to spend most of our time working with that. Okay. The next easiest thing is the linear shift variant system. So as long as things are linear, there's a lot of stuff we can do. When they start becoming nonlinear, it becomes harder. We'll put it that way. And so a lot of times, even if you have a nonlinear system, you will try to approximate it as linear because it just makes life so much easier. Okay. Okay. Now, we're going to look at a couple of examples here, and we're going to use the polling feature. So actually, let's see. Not that one. Yeah, so this is like a new thing that I'm trying out. Seems pretty good. So, okay. So this is system 1. We'll set that off in a second. And so this is an input, basically a series of rectangular pulses. And this is the output. And then we're going to do another experiment and give it a sinusoid as input. And we get a sinusoid as output. In fact, doesn't look all that different. And then I'm going to put the sum of those two things in, and we get something out there. Okay. And so this slide basically puts all that together. I didn't used to do this, but I decided this would be easier. So again, for this input, we get that output. For this input, we get that output. And then this is the sum of these two inputs. And this is the output that comes from that. Question in the polling will be linearity and shift invariance. So take your time and think about it. And of course, with linearity, we aren't, this is a very limited experiment, so we aren't trying everything we could possibly try. But the question is, are there any suggestions that any of this is not true? All right, keep them coming. Couple more. Okay. The results are in. And votes are 100% in favor of linear. Good. Well, what you expect with linear is that basically the output of this should be the sum of these two guys, right? If it's not, then definitely we are nonlinear. The shift variance, shift invariance is a little, well, it really depends primarily on observing this one, right? And, does the response to each of these rectangular pulses look the same? Now, they look a little bit different just because of the graphing, okay? If you look at them like super close, but basically they are the same, right? They are the same height. They get kind of blurred a little bit where the corners kind of round off, but for the most part, they're all the same. And so this system would be, at least appear to be, shift invariant on the basis of that observation. It's a lot easier to see with this one, maybe, than with this one, but yeah, all of these should look the same too, right? As well as, you know, every identical period of this periodic function here. Does anyone have any questions about that?
So that one's shift invariant, right?
This is shift in linear and shift invariant. That is right.
Could you please explain why it's shift invariant?
Yeah. Okay. So shift. This experiment. This part of the experiment is the one I'm going to go over to. Where? Oh, I'm going the wrong way. Sorry. Okay. I'm going to go to this experiment and show it a little bit closer. Okay, so the idea here is that we're putting in the same rectangular pulse at different times. Okay, and if the system is shift invariant, then it should respond in the same way to all of those identical rectangular pulses. It should give us the same waveform as a result, merely shifted in time by the same amount. And so really the observation to make here is, okay, do I get, you know, are all of these identical when I put identical stuff in at different times? Do I get identical stuff out at those times? Does that make sense?
Yeah, got it. Thanks.
Okay. Okay. So this is a linear shift invariant system. I know that because I wrote a program that makes it, and it is linear and shift invariant. Okay. System 2. So this is a different system. We're going to use the same inputs, but clearly we get different things at the output. Okay. So our rectangular pulses give us this. Our sinusoidal input gives us that. And then the sum gives us this thing. Okay, and so now we're going to ask the same question again. Linear or shift variant invariant. Okay. Keep them coming. One more. And yes, the results are in. Okay. Oh, we're all over the place this time. Okay. So votes are in favor of nonlinear and shift invariant. And well, someone who says nonlinear, jump in and explain your reasoning.
So I was looking at G1 of t and G2 of t, and it doesn't look like G3 of t is the sum of G1 of t and G2 of t.
Absolutely. You can kind of tell that by this peaks at 0.2, this peaks at 0.8. So the sum of those two things could never be greater than 1, and yet it's like 1.6 here. Okay. So this is, in fact, nonlinear. Now, someone comment on shift invariant. I guess the majority says shift invariant. Why? Someone comment why you observe that.
Is it because when you put in the same input, you get the same output?
Yeah. So you get the same response from each of these guys. Now,
for each of the inputs.
Yeah. So, but now one thing that might have that sometimes throws people off a little bit is the fact that there's a delay. Okay. So this one, you know, starts at time 0, but its response doesn't start until sometime later, around time 1. Well, it starts around maybe time 100 or so. But that's okay, as long as that delay remains consistent, right? And so basically, each of these produces one of these little pulses, okay, but at a later time, but the time delay is consistent. Does that make sense to everybody? You can see the time delay happens here too. Of course, it's the same system. So this is a system that is, yeah, the votes are correct here. This is a system that is nonlinear, but shift invariant for the reasons that people observed. And the fact that there's a delay is okay. In fact, that's going to happen in pretty much any real system that we actually create. There has to be a delay because things can't happen before, you can't respond to an input before it happens, right? Time only moves one way for us. You know, that's a thing that's not true like in images, right? You can go both left and right in an image, up and down. And so that is the concept of causality, which you've probably heard about. And so that doesn't apply in areas maybe other than time. But when we deal with time domain systems, and especially real-time systems, we only go one direction. And so very often real systems will always have a delay built in. Okay. Any questions on that? Okay. Okay. So this is one nonlinear. And again, I know that's true because I wrote the program that makes it. It has an x squared in it, right? So if there's an x squared, then that's going to be nonlinear. Okay, well, I think we're starting to get the hang of this, right? So here's system 3. So again, same inputs as before. We get this output now for this system. We get this output for the sinusoid and then the sum. So let's go ahead and relaunch that poll. Two more. Okay, they're all in. Hey, here's a question. I just don't know. Do you guys see this polling result when I'm sharing my screen?
No, we don't.
No.
Okay. I have a little window like right here where I'm moving my mouse around. I didn't know if you guys could see that or not. Okay. There. So that's the result. Okay, and so, you know, votes are definitely in favor of linear and shift variant. Okay, so, you know, based on everything we said before, shift variant is suggested by the fact that these are different, right? Because, you know, again, we put in each individual rectangular pulse, but the system responds a little differently to each one of those as a function of time. So basically the same thing happens here, right? The sinusoid is modulated in some way with respect to time, and that would happen here too. Okay. So the fact that it's shift variant is really what you observe from here. Linearity, again, comes from observing that, well, hopefully this is the sum of these two things if you kind of look at it. And yeah, maybe poor practice here for letting this go off the end of the graph, but hopefully you get the idea that that looks like the sum of those two things. We're peaking about 1.8 here, right? And this is about 0.9, 0.9. Yeah, and it is linear, but shift variant, again, based on the little program I wrote to make that happen. Okay, does anybody have any questions about those observations? Is that okay? Okay, so this is one of the other permutations, right? It's linear, but its response changes with time, depending on what time you happen to access the system, you might get a different result. Okay, which is, you know, which may be disturbing unless you have some way of characterizing how it changes with time, which is usually the way we would handle a system like that, is we try to understand how it changes with time.
Can I actually ask a question about the shift variance?
Yeah.
If instead of sending it like the signal in pulses, if instead you just had like for F1T, you just had it as like a giant block that was like consistently a 1, would you still be able to witness the shift variance, or does it have to be like individual pulses that you witness their specific response?
Yeah, so I would say you wouldn't be able to conclude one way or the other on that, because you know, basically that would be like one event. Okay, and in order to be able to observe this, you basically need to be able to observe the same input at different times. Whereas if you had one long rectangular function, you really wouldn't know, you know. So let's say you put in one long rectangular function, and let me get my thing here. Let's say we put in one long rectangular function. Whack, sorry. Sometimes the button on the pen causes me troubles. There, okay. Like that, and the output, of course, it would be scaled much more, but let's say we got an output that looked like this as a response to that thing. You really wouldn't know if, well, if that's the response to that rectangle, or, well, that is the response to that rectangle, but you don't know if that's because the system is changing its, say, its gain with time, or that's just what the normal response to that would be, you know. So the way to find out would be take that long rectangular function in and put it in at a different time and see if you got the same thing. Okay. So it would be hard to parse it out.
All right, thank you.
With that. Yeah, good question. Okay, last one more. Okay. watch the poll again. Okay. Okay, so again, our rectangular pulses, and this is our output. Sinusoidal pulses, that's our output. And then this case, so there's all of them together. See what you think about this one. Okay, two more. And we're done. Thank you. Okay, so the overwhelming, well, so linearity seems to be popular. And that's good because this is linear, okay? And shift invariance, a little less certain. So we'll talk about that one because that's kind of the key to this one. So linearity, again, you know, all we can really do is observe, does this appear to be the sum of these two guys? And it kind of does. So I agree with the discussion of linearity. Now, someone who said shift invariant, why don't you jump in with your reasoning on shift invariant?
I wasn't super sure when I put shift invariant.
Mm-hmm.
Like I actually wanted to modify the answer and kind of say shift invariant within like the specified range.
Okay.
Because like when there are steady like pulses, I guess, it seems to be shift invariant, but the ends are kind of weird.
Well, exactly, right? So if you go, you know, strictly with the rule that every event should look identical, well, they don't, right? Because they look different at the beginning and the end.
Mm-hmm.
But here's the thing about this one, and this is always a tricky one, but it makes an important point. The response to one of these, let me get my pen going here. Okay. The response to one of these guys, well, starting at time 0, looks something like that. That's the response to one of them. Okay. And so what's happened is we brought in the second pulse before the first one's done. And so as a result, we get an overlap between these two guys. Because the second one, you know, happens here, and they overlap and overlap and overlap until we get to the end, because there's no more left to overlap, and the last one trails out. So as a result, this system is actually shift invariant. Okay. Part of the problem was this wasn't the best experiment for this particular system because these guys are spaced closer together than the length of the response of the system. Right? Again, nothing says that the system can't take as long as it wants to respond. Okay, and the fact that it's linear means that these two guys kind of add together in the places where at the times where they overlap. So the first one's not done yet, and then it starts responding to the second one, but that's okay because it's just going to add their results together since it's a linear system. Okay, so what we're seeing here, the fact that these might look a little different is the fact that they're overlapping here in the middle. Does that make sense? So this system is linear shift invariant. And again, this is actually an important part of the point of where we're going with linear shift invariant systems is that, the inputs, if we start thinking about the inputs as being composed of lots of kind of elemental pieces, and we break up the input into a sum of these elemental pieces, well, the output is going to be the sum of all of the responses to those elemental pieces, but they're going to overlap in time. They won't be so distinctive, really, right? That's basically the way these systems are going to work. So we're going to see a lot of overlapping in time of responses. Okay. So this is one of the more challenging ones, and for a purpose, okay, is to make that point. Overlapping is perfectly cool, and the overlapping is just going to add together. Anybody have a question on that? Okay. All right, this is a good time for a 2-minute break. So I think we will do that. Let me see if I can, yes, keep that. So yeah, 2 minutes to stretch. I'll bring up my silly timer. Okay. Have a stretch. Whatever. Okay, we're back. Okay, so hopefully at this point we have an idea of what we mean you know, in a practical sense of what you can see of how these systems behave. Now, we're actually going to start most of our discussion with discrete systems because I think that's easier to see what's going on. So remember, discrete systems are, you know, at specific time points. So we have a system. We put in a impulse. Remember, the delta function or unit impulse should be a familiar function. Basically, the delta function usually looks like that. We draw it with a straight up arrow, and basically the definition of delta of t is that it equals, well, mathematicians wouldn't like this, but I'm going to go ahead and say it anyway. Its actual value is, well, you know what? Sorry, that's the continuous one. Gotta fix that thing. Okay. The discrete delta function is equal to 1 when t equals 0, and it's equal to 0 otherwise. Okay, so actually, I'm going to do this just a little bit differently. The discrete delta function we do with a little lollipop instead. Okay, so delta of k, and this is a value of 1. Okay, this is the continuous one. We're not talking about that one right now. Okay, so that's the delta function. Okay, and we get some function out, h of k. Okay, some discrete output for that. So if we instead put in an impulse at time a, so this function, but we shift it to time a, go ahead and, well, I'll just see if anyone wants to jump in with what do we expect the output to be? Anybody? Come on, be adventurous.
Is it h of k minus a?
H of k minus a. Well, okay, kind of a trick question. So I didn't tell you it was shift invariant. So technically, no. The answer is we don't know. However, if it is shift invariant, yes. So I'm going to say, my pen's getting a little sensitive here, sorry. If shift invariant. Okay, so if it is shift invariant, yeah, we expect that impulse response. Okay, and might as well get used to this idea. H of k is what we refer to as impulse response of the system. It's basically whatever you get out of the system if you put in a delta function. Okay, and so we expect that to shift if it's shift invariant. If it's not shift invariant, we don't know what that is. Okay, because we can't guarantee it stays the same. Okay, well, if we let the input then be a sum of impulses, right? So the idea is now we have an input that maybe is a weighted sum of impulses, something like that, where this is and maybe more after that, but you get the idea. And they're basically weighted by this function x. So this is x at 0, this is x at 1, and so on and so on. Okay. If that's the input, then if the system is linear, how do we write the output? Well, let's not worry about writing it just yet, but just conceptually, if the system is linear, then the output is the sum of the response to this guy with the response to this guy with the response to this guy, et cetera, et cetera, et cetera, right? The individual responses are all going to add up, even if they overlap, okay, if the system is linear. Okay, and so, writing that response is a bit of a challenge. So we're not going to worry about writing that just yet, if we say linear only. But if we add, if the system is shift invariant, okay, so I'm going to say, if it's linear and shift invariant, then what's going to happen? Well, okay, each of these guys, each of these individual ones is going to generate an h, right? An h of k at its position. And so basically every delta of k minus a produces an h of k minus a. And again, to be clear, if it's linear shift invariant, that's true. Okay, well, if it's shift invariant, then every delta produces an h of k minus a. So as a result, if it's linear shift invariant, then y of k, because that's the output, right, is equal to the summation on a of x of a, oops, h of k minus a, right? I mean, that's basically what linear shift invariance just told us. Everybody agree with that? Okay, so that's pretty straightforward. And by the way, that might be familiar as a convolution. Okay, in this case, it's a discrete convolution. And so, going back to linear systems course where you learned what the convolution is mathematically as an integral, or maybe as a sum, and maybe did some silly graphical convolution where you kind of flip it and shift it across. Did you do graphical convolution? Yeah, I hate that. It's horrible. I had to do it too, because that's the way people have always taught this. But it doesn't make any sense at all as to what's going on, okay? I think this makes more sense. When you look at it from this perspective and you say, oh, here's what's happening when we do convolution, or when we characterize a linear shift invariant system, every individual element of the input is producing its contribution to the output. Now, the fact that it's shift invariant means that that contribution doesn't really change with time. And the fact that they're linear means we can add all of their individual contributions together. Okay. So this says, okay, well, I can just, for a linear shift invariant system, I can take my input, break it down into elemental pieces, in this case, individual delta functions, but they could be other elemental pieces, okay? As long as the input is just a sum of those elemental pieces, find the outputs to the elemental pieces and then add them back together. Well, that's what convolution is doing. Okay. Anybody have a question on that? Okay. So that's one reason why we're, linear shift invariance is so closely tied to convolution. If we don't have linear shift invariance, this isn't true. Okay. What you can say is that H let's say your linear shift variant, H changes with time. You can still do this, but all the H's are not the same. Basically, H becomes a function of time. And so it's a good bit more complicated. We're not really going to go there. But you could do that at least. That would be better served with a matrix operation. Okay. So bottom line, right? If linear shift invariant, then all these different ways of writing how the system works as a system operator operating on the input X, or breaking it down this way, or writing it with the little star, which is usually the operator we use for convolution. That's what we get. Okay. And in a continuous system, we have the continuous convolution integral. Okay. And here, this is why I do discrete first, but basically the idea is that in a continuous system where basically, your input is defined at all times, we are still sort of breaking that down into a sum of individual little delta functions. They're just spaced, infinitesimally close together now. And therefore it becomes an integral rather than a sum. Okay. So, again, mathematicians probably wouldn't like this, but conceptually, the idea is that, if I go back to this, if we start bringing these individual pieces, elemental pieces, closer and closer together to where they're extremely close together, then we get essentially a continuous system. And the same idea holds. Okay. Does that make sense? Okay. The other thing that comes out of this, and again, this is a kind of a fundamental thing from linear systems course, is that if this system is linear shift invariant, the only thing we need to know about it is this, H of K, its impulse response. And again, if it's continuous, it's H of T. If it's discrete, it's H of K. But that's all we need to know in order to find the output for any input, right? Because again, we have the convolution integral, and whatever I put in, if it's linear shift invariant, I just convolve it and I get the output. Okay, and again, that's why this much simpler. Just again, to make the point, if it's linear shift variant, then H of K is also a function of, well, we'll say the absolute time variable. I won't give it a name, but sorry, absolute time variable. It's a function of two things. Basically, you get an impulse. You would characterize that as having an impulse response that changes with different times that you put the input in. Okay, and so it basically, is a two-dimensional function rather than a one-dimensional function. Okay, any questions? fundamental result. Basically, that's all we need to know. If we know that, and we know the system's linear shift invariant, that completely describes it. Okay, and again, I draw these systems as kind of black boxes. We aren't really concerning ourselves so much with what's inside the black box. Could be circuits, right? Or anything, could be a computer program. But if it has this input-output relationship, that's all that matters. Okay. So we got that far. We will carry on a little bit more next time with Fourier transform, but we'll kind of just get started with it. There are lots of different Fourier things, we'll say, that pop up in different ways and that apply to different kinds of things. Okay? And again, this is not, I don't expect you to memorize this or anything, but you may have, in differential equations class, you may well have seen Fourier series, okay? Because that can be used to solve certain differential equations like wave equation and things like that. And it has continuous and discrete forms, okay? But also, we just talk more generally about Fourier transform in kind of signal processing and in linear systems and so forth. So, I mean, all of these are related, right? And we will kind of go into a little more detail later, especially when we talk about the discrete versions of these, about some of the relationships that are important practically. I will preface this by saying that I don't ask you to do Fourier integrals, okay? So I don't ask you to actually compute Fourier transforms. I will ask you to use tables and properties of Fourier transforms maybe to kind of figure out some things, but I don't expect you to actually sit down and calculate any Fourier transforms, okay? So this is, mathematically defines the Fourier transform. Basically, it is taking your time domain function and integrating it with this complex exponential e to the minus j omega t. And as you recall, e to the minus j omega t, which was on our pretest, from the Euler relation is equal to cosine omega t minus, in that case, j sine omega t. And if we think about, what that function is in time, it is a sinusoidal function of a particular frequency omega, coupled with an imaginary component, which is another sinusoid of the same frequency, but 90 degrees out of phase, right? Sine and cosine are 90 degrees out of phase with each other. Okay. And so those are kind of the elemental functions of the Fourier transform, which we will look at a little bit more later. So that's the definition. There's the inverse Fourier transform also, which basically means we integrate with the complex conjugate of that. Remember, a complex conjugate negates the imaginary part. So these functions are related. It's just the 90-degree phase shift goes the other way. Okay, and there are various ways of defining where somewhere in the process there's a 1 over 2 pi. Okay, so usually usually I put it in the inverse transform, and you just have to be consistent. Sometimes people will put like 1 over root 2 pi in the forward transform and 1 over root 2 pi in the inverse transform, so they're scaled the same. Again, we're not really, I don't care, honestly, and we're just going to do whatever MATLAB does. All right, so, all right. So that's just introducing it. The discrete form basically is similar. It's just that these are discrete sinusoidal functions now, right? They're defined at certain values of k, where k is an integer. And we will dig more into that, I think, next time. But there's one thing I want to point out before we sign off, and that is on our course page, assignment 1 is posted. Well, I mean, they're all posted, right? But assignment 1 is due a week from tomorrow. Okay. And I know, probably you won't start on it right away, but you can if you want to. So, and then the other thing I want to point out is one of the things that is useful to know, be familiar with, are the properties of Fourier transforms. And so as a result, I would ask you to, before next time, you're not going to turn this in, but take a look at and be familiar with and actually maybe find some of these Fourier transform properties for next time. Some of them aren't things to fill in, but are things to just make sure you're familiar with, like the symmetry relation. And let's say Parseval's theorem, it's already there, but the significance of it is what I want to talk about next time. So just, again, fill in the ones that are not filled in, and just, again, you can go search on the web for a lot of these things. And we will kind of go through this hopefully quickly next time, and just make sure you're familiar with those things, because we will refer to those quite a bit, because in many ways we're kind of reasoning our way through a lot of these things instead of sitting down and calculating them, and the properties are going to be really helpful with them. Okay, anybody have any last questions? In that case, we can sign off. I will stop.